Okay, so welcome everybody, and thank you for being here. It's a pleasure to have today Junhwa Hur. I hope I'm pronouncing the name in the correct way. Is finishing his PhD at TUD, where he works with Professor Stefan Roth, and he is mainly interested in dynamics in understanding, and in particular in the jointly estimation of motion, depth, and semantic segmentation using in particular self-supervised learning techniques. So please.
Okay, can you hear me?
Yeah, we
Oh,
can.
yeah, that's good. Okay, so I'll start. So thank you for inviting me for the seminar. So I'm, my name is Junhwa Hur from TU-Darmstadt, and I'm almost finishing my PhD. So today, I'm going to explain about self-supervised learning of depth and motion estimation from molecular images. So for the last recent few years, there has been increased attention for estimating some ill-posed problem only using from monocular images, such as one can estimate depths out of these two images and camera motion, and also optical flow jointly, as well as moving object segmentation and even scene flow. So, of course, using CNNs. So in this seminar, I'm going to explain how each objectives can be obtained or estimated using CNN and trained in self-supervised manner, and how which kind of proxy tasks or which kinds of proxy losses has been investigated so far. So first, before starting, we can ask a question by ourselves uh, and why we are using self-supervised learning. So the first and the most important reason is that in the real world data set, we don't have much quantitative data available. Of course, we can somehow obtain some depths of ground truth annotation for depths, like using LiDAR scanner. But the other task, like optical flow or for scene flow, is not that easy to obtain the dense annotation for those tasks. And secondly, of course, we can use synthetic data set for training this network, but there's always domain mismatch exist. So the network trained on synthetic data set doesn't perform well in the target domain. And there have many recent work that actually self-supervised training on the target domain is similar or sometimes outperforms the method that uses pre-training on synthetic data set. So many methods are following the self-supervised training method, and then later on then can be fine-tuned on the target domain using available ground truth as well. So if assuming that we have the ground truth data for depth, optical flow, or other tasks, we can train like this using supervised loss. So from the input frame, we pass this input frame to the CNN network, CNNs, and then for the output, we can always apply the supervised loss. But unfortunately, those ground truths are not available in the real world, or only limited amount. So in a self-supervised manner, many methods have devices proxy task using view synthesis, which is that given another view like the target frame, they try to reconstruct the source frame given target frame and the estimated depths, optical flow, and pose using geometric relationship. And then given the reconstructed source frame, they apply the unsupervised or self-supervised proxy loss between these two frames. Then what happens is that the network tries to reconstruct this source frame as similar as possible to the source frame, and which guides the network outputs the correct combination of depth, optical flow, and camera pose that is formalized by the proxy loss. And the later slide, I'm going to talk about how those proxy losses are formalized. So first, as a first task, we can first, let's see how these depths can be estimated from monocular images, which is Ilpo's problem. So 3 years ago, Godard et al. In CVPR demonstrated estimating depths from a monocular image using a stereo image pairs. Actually, it's not the stereo matching problem, but it only uses stereo images in the training time, and in the test time, it only uses one single monocular image to estimate depths. So how it does is that first it inputs the left view. So assuming that we have a stereo image, left view and right view, and it inputs the left view to the network and outputs to us, and it let the network output disparity. And then it designed a proxy task that, given the right view, it reconstructs the left image and then applies the proxy task, apply the proxy losses that between the given left image. And here, unsupervised loss consists of brightness constancy, so photometric losses, and also the smoothness loss, which has been used many times in the classical energy-based method. So more specifically, how it reconstruct the left view is following. So given for each pixel in the left view along the scan line, for each pixel, we define the corresponding point in the right view using the estimated disparity from the output from the network. And we look at the intensity value of this pixel and then warp this intensity back to the original pixel coordinate. Then if the disparity is correctly estimated, then the pixel value of this original right pixel and the right pixel should be the same. So they minimize these brightness differences between these two pixels so that the network outputs the accurate or corresponding disparity that satisfy this loss. So here is some nice animation that how the network is optimized during the training. So in the beginning, network just outputs random disparity, and using this disparity, we can reconstruct the left view using the right view and the disparity. And we apply the unsupervised loss that minimize the brightness differences between the left view and the reconstructed left view. Then the network tries to generate the reconstructed view, left view as similar as possible to the left view, and correspondingly, the network tries to estimate the corresponding disparity map. So for instance, this can be the last result or final result of the network that estimates fairly clear disparity map using the proxy loss. And of course, the objective is to estimate depths. So in this pipeline, the main assumption is that the focal length and the baseline of the stereo rig is given, so that this disparity can be converted into depths finally. And in another line of work, instead of estimating depths purely, there's another work that estimates depths and pose jointly. So previously, the method estimates depths using the stereo image only. However, you can only estimate depths using jointly estimating camera pose. And this line of work is more challenging setup because it uses a sequence of molecular images. And here is how it does as following. So it has two networks are coupled, and there are two networks that estimate depths and pose jointly. And given the output of the pose and the depths, it reconstructs the current frame by using the output and the next frame. And here is how these losses are formulated. So first, for each pixel in the current frame, it back projects the pixel into the 3D space, assuming that the camera calibration matrix given. And using the estimated depths from the output, it can estimate the 3D point of each pixel from the current frame. And then it applies the camera pose transformation from the network output. And then it projects the 3D points into the next frame, and which becomes the P prime. Then we can find the corresponding point of each pixel from the current frame, the next view. And the thing is, the pixel intensity between these two corresponding points should be the same. And they penalize these brightness changes between these two corresponding points. However, if the depth or camera pose is not accurately estimated, so for example, if the depth is estimated like this, then the corresponding points will arrive in different positions that occurs higher photometric losses that the network tries to minimize. And vice versa, if the pose is estimated differently, as it's supposed to be, then the corresponding points arrive in a different pixel, and the network, in the end, minimize these losses. So here are some two qualitative comparison between the two methods so far. So first one is using stereo images, and the second one is only using monocular images, which is more challenging setup. And looking at qualitatively, of course, the first method outputs more clear depth boundary, and also it estimates human fairly well. Of course, it's not perfect, so much better than the monocular image-based method. However, it doesn't mean that always the first method is better than the second one, because here are some comparison. So first, when using stereo images, it actually apparently has an advantage that it estimates depth using a stereo image, so it gets some assistance from the stereo image in the training time. So actually, assuming that the stereo rig is fixed, it can always determine the correct scale of the object, because the right view of the stereo images guide to accurately estimate the scale of each object. So it can be learned or memorized, vice versa. However, when only using monocular images, the scale cannot be easily determined, because we don't know actually the scale. It's not really possible to correctly estimate the scale. However, and another pros of the first method is that it only uses single CNN, which is always can be better to train, it's more stably trained. However, the second method uses depth CNN and pose CNN, and they jointly train each other. And usually when training multiple CNNs together, it always happens that sometimes one CNN dominates the other, so the other network sometimes outputs some trivial solutions that only minimize the losses. So it's not always joint training is not always can be easily trained. And another comparison is that the second method assumes that all objects in the image are static and only camera moves, and we can only observe the relative motion caused by the camera motion. So it cannot really handle moving object. But on the other hand, the first method can use a stereo image that is captured at the same time, so it can handle. It doesn't have to be. It doesn't have any problem of handling moving object or not. However, as I said before, it's not always, the first method is not always good, because it requires stereo images in the training time, which is not always the case in the real life. But on the other hand, And the second method doesn't require stereo images, but it only requires a single monocular video, which we have already heavily enough in the online. So you can always exploit unlabeled video data for training. The next thing is that, so in the so in that sense, the second method has some advantages, but it still has some limitations. So after this work, many methods proposes to overcome the limitation of the second method has. So the first one would be handling moving object. So one easiest way is that in the training time, we can try to ignore this moving object and only include static object for training the network. So last year, Godard et al. Proposes an auto-masking trick or strategy that it ignores the moving object pixel in the training time, and it only trains the network using the static object. But detecting moving object is not always easy because then it can be a chicken-egg problem that we want to estimate moving object to detect moving object or so. So what they do is so given a temporally two consecutive images, they simply subtract these two temporally consecutive images frame. Then, for example, in the moving scene where the car moves forward, then in that case, some moving object with a parallel motion with the camera would stay still in the scene, although the camera is moving. So this car, the intensity differences between the two consecutive frames will be like this, and it has only some moving object will have some black pixels in the different images. And then it can be a kind of pseudo way of detecting moving object in the scene. And then they only include proxy loss or of this white pixel in the loss. And in the other case, in the static scenes, camera is not moving, so many static scenes will be black. And actually, when jointly training depth and camera motion network, static scene is not always good to include, because in that case, anything is not moving, so it's not possible to correctly estimate depth from the static scene. So they chooses to discard this kind of static scene by using this auto-masking strategy. And here are some qualitative examples of this strategy. So there is as a comparison, there's two methods called GeoNet and EPC++, which some of them will be introduced later. So you can see that in Godard's approach, you can correctly estimate the depth of the car here by using this auto-masking strategy. And on the other object, sometimes the depth Q of the car the network says that this car will be far away, which means that usually in this driving scene, the car in front of the camera approximately move the same speed, so it remains still in the video. But usually some objects that is located far doesn't move at all, so it stays still. So networks think that these objects move still, which means that in that case, this object is located far away. However, some ignoring those moving objects is a kind of good idea, but it's not always a good idea, because if we actually model this moving object with some assumptions, then it always gives other more informative information that, for example, we can model a camera pose more accurately, and also as well as a side product, we can also do the moving object segmentation. So there are a couple of approaches or actually many approaches that tackle this problem and tries to actually explicitly model the moving object. So for instance, 2 years ago, CVPR, Ian et al. Proposed a called GeoNet, and their pipeline is as follows. So the first end of the pipeline is the same, that they have depthnet and postnet, and given the estimated depth and post, they calculate the optical flow induced by the camera motion. However, in that case, it assumes that all objects in the scenes are static, so this so-called rigid flow is only induced by the relative camera motions. And then after that, in order to handle this moving object, they concatenate a so-called res flow net that estimate residual optical flow on top of this rigid flow. So this res flow net, so-called res flow net, supplement some independent moving object that is not captured in the rigid flow. And in this pipeline, they apply the proxy loss like followings. So they first introduced the view synthesis loss for to estimate optical flow, and also smoothness loss for depth and optical flow as well for spatial smoothness on the objectives. And finally, they also include consistency loss by calculating the forward and backward optical flow jointly, and then only reinforce the consistency between them for only inlier pixels. So in the optical flow cases, how to reconstruct the current frame is as follows, which is actually the similar case of the disparity or depth estimation. So for each pixel in the current frame, P, it finds the corresponding points in the next frame, given the estimated optical flow, and then it warps the intensity of this pixel back to the current frame. Then, of course, if the optical flow is accurately estimated, then the intensity of the pixel P and the pixel prime, which is P plus optical flow, should be the same. So they minimize the photometric losses between these two corresponding points bound by optical flow. So here are some qualitative results. So left one is optical flow map, and the right one is error map visualized. So in the error map, blue color means that optical flow is accurate, and becoming red means error is higher. So only when using the rigid flow, which is calculated from estimated camera pose and depths, car shows here, in the car shows a higher error because it moves independently, and thus the depths and camera motion cannot correctly capture the optical flow of the car. However, after plugging the residual flow net that estimates the residual motion, it can supplement the rigid flow and correctly estimate optical flow. So there's another work called competitive collaboration that also do the same job and in the similar pipeline. They also have depth network and camera motion network, and then they have optical flow network as well. And then they even have a motion segmentation network that detects the moving object, which has a lot of networks. And then in the training time, they demonstrate a loss that combines all of the output of the network and then jointly train. Of course, jointly training those networks is not easy because sometimes one network can dominate the other, so the other network cannot be properly trained. So in that work, they demonstrate some training scheme called competitive collaboration, that sometimes they fix some network and then train another. And then after that, after a few amount of iteration step, they fixed another network and then train back to some network. So like a coordinate descent optimization problem back in the days. So in summary, like from the beginning, so after having more objectives, we can accurately estimate some sub-tasks, and also we are able to handle moving object, which is good. However, it has a lot of disadvantage, which is that, so for each task, we include more and more network for each objectives. So we have more CNN, which is sometimes okay, but not so ideal, because the number of network parameter increases, and also jointly training those network is not easy. And then in order to design the proxy losses, so we always include more and more loss functions. And actually these losses are handcrafted as well as these hyperparameters. So as we have more proxy losses, then it means that we have more hyperparameters to tune. Actually, these hyperparameters can be automatically tuned, but for many papers, they usually set this parameter by hand. So like back in the days when we use classical energy-based model and using like MRF or CRF, these parameters can be easily tuned by like using grid search or hyperparameter search. But in the setting of CNN, it has to train all of the network from the beginning to the end, or like partially. So it takes more time to find the correct parameter setups, which can be another interesting problem to solve in the future. So far we have seen how those joint objectives can be obtained, but as a last objectives, we looking for monocular simflow setup as a final task, which is a high-level task. So this year, with my supervisor, we proposed a self-supervised molecular simflow method that estimates depth and simflow out of the 2 molecular images, which is highly opposed problem, because for a single 2 images, it's not the depth, it has a depth ambiguity as well as scale ambiguity. So it's not easy to determine the depth and scale from the single image, and also the 3D motion as well. Also, in case of occlusion, it cannot really easy to determine the correct 3D motions where the depth Q is not available. So, of course, one can say that, however, from the previous method that estimate jointly depth and optical flow, we can maybe reconstruct simflow out of their estimation. So, for example, we have optical flow between these 2 corresponding pixels, and then we also have depth Q for each pixel. Then we can back project these 2 points into 3D space, and we get the 3D points for each pixel. And after subtracting these 2 3D points, we can directly calculate the simflow, which is fine. However, it's not always the case, because if occlusion happens, then in the next frame, we cannot get the depth Q for the occluded pixels, which means that we cannot recover simflow by combining these 2 depth map of each frame and optical flow. So here in this work, we present to this estimate depths and sim flow jointly using a single network. And we introduces two novel losses for estimating depths and sim flow together. So one is first adopting proxy losses for disparity estimation from Godard et al. And then another proxy losses is view synthesis loss and 3D reconstruction loss that guides the network to estimate the correct combination of depths and sim flow. So the losses are in detail as follows. So for view synthesis loss, we first backproject each pixel using estimated depths, and then we translate these 3D points using estimated sim flow. And then we project this point back to the image plane, and then this corresponding point should be the same. So by penalizing these two photometric laws, it guides the networks to estimate correct combination of depths and sim flow. And also, not only in the 2D space, we also penalize the 3D distance between the two corresponding points. So given the translated 3D points, we also back project these 3D points in the target frame to the 3D frame. And then the thing is, this 3D point should be in the same 3D point. So we penalize the 3D point, 3D distance between these two corresponding 3D points so that the network estimate correct combination of depths and sim flow. So for example, here is the reference image and the reconstructed image, and as well as target 3D points and the reconstructed target points. And the more important thing is we only apply these losses for only visible pixels by using the occlusion map detected by backward sim flow. So for instance, this tab is quite important, we find. So for example, here are some examples of current to given frame. So the current frame and the next frame, and then the last one is the reconstructed current frame from the next frame. So CNN tries to reconstruct the current frame using the next frame. However, the yellow car is moving forward, moving towards to us, and here the pixels are occluded in the next frame. And from the next frame, we cannot really reconstruct this view. However, CNN is quite good at doing the job given the losses. So although it's not visible in the next frame, CNN somehow tries to reconstruct these occluded pixels. And actually, maybe it refers some nearby pixel around somewhere, not in the correct positions. However, our objective is not to reconstruct the current frame, but actually we want to have some accurate optical flow and depths. So it's important to discard this occluded pixel so that this pixel doesn't affect the loss function to train the network. So we discard these occluded pixels, the proxy loss functions, to have more accurate result. So here are some qualitative examples that estimate two optical flow and sorry, excuse me. So here is the qualitative examples that estimate sim flow and depths, and we visualize it in 3D. I guess the video doesn't play. Yes, but it's somehow it's slow. So as given the estimated sim flow and depths, we lift the camera position a little bit up and then visualize the 3D space of captured by the camera or captured by the two frames and using estimated sim flow and disparity depths or disparity from the CNN. So if I have a brief summary so far, so we have seen how each objective can be obtained by using the defined proxy loss. So when comparing the SimFlow approach to the previous approach that estimate depths, pose, optical flow, or moving object jointly, it clearly has some advantage and disadvantage. One advantage is that directly estimating SimFlow can substitute some soft task. For example, depths can be obtained and optical flow can be also obtained by just projecting SimFlow into 2D space, or the camera motion can be also estimated by using some robust estimator using the SimFlow directly. So it somehow simplifies the multitask learning approaches by only tries to estimate SimFlow. So we devised to use a single CNN module, which we find interesting and efficient because it has less number of network parameters and also easy to train, because instead of just having more networks and jointly train, which always become a problem. But it still has some disadvantage or limitations that is still based on some complicated or handcrafted proxy losses that require also some hyperparameter tunings. So as the last section of the seminar, I'd like to mention about some possible future directions, like for having better accuracy and whether we can use other things instead of proxy losses that is designed by hand. So there is an interesting work this year that Junhwa Hur et al. Demonstrated a series of ablation studies on the proxy loss for unsupervised optical flow learning. So this work have demonstrated a series of ablation study on the proxy losses from the past a lot of works. So, for example, for learning optical flow in a unsupervised or self-supervised manner, many methods have demonstrated really different kinds of proxy losses choices. And this paper demonstrates which losses or which design is actually critical for having better accuracy. So for example, this proxy loss consists of photometric loss, smoothness loss, and occlusion handling strategy, or what kind of input resolution is important, or which kind of data augmentation or pre-training is important. So this paper analyzed and systematically analyzed each losses and figure out and suggest which design is better and which design is not important at all. So the conclusion is that for having better accuracy, actually designing better proxy loss is important, because this is the loss that the network relies on in a self-supervised manner. But on the other hand, it means that the accuracy is bounded by the proxy losses. So it has clearly limitation, because we cannot always design these losses by hand. Yep. So for now, this proxy loss is important and matters for the accuracy and the type of objectives. But usually, as many as we have the proxy losses, which means that we have more hyperparameters to tune for jointly combining these losses in a weighted sum manner. So for now, as I mentioned before, those hyperparameters are tuned by hand, but actually we can also effectively use hyperparameter optimization so that we don't have to train the network as so many times many times to find the correct configuration or combination of the hyperparameters. And another thing is that instead of using some handcrafted losses, we can also use some feature metric loss. So there are some couple of works this year that instead of using the in the photometric loss, instead of using a handcrafted energy model, it uses feature metric losses. So here in the left network, they have a separate network that encodes some feature map from the input image. So how they train is that it's kind of autoencoder network that it inputs an input image and then it tries to reconstruct an image and apply the photometric loss between the reconstructed image and the source image. Then this network somehow learns some internal representation of this image, and given this network, they apply this encoder to the training, and after getting the feature map, they compare the feature map between the feature map of reference image and the warped or reconstructed image. In that case, maybe the feature map has more representation power, so maybe it's a hypothesis that it has some semantic meaning, or depends how it trains, it has more representation capacity, so it can be also a good idea to substitute some handcrafted losses. And finally, we can also try, instead of just purely relying on self-supervised learning, we can also use semi-supervised learning. So in Europe's 2017, Lai et al. Demonstrated a semi-supervised learning method for optical flow using GAN. So what they do is as follows. So they train a CNN to estimate optical flow, but combining using synthetic data set with ground truth and unlabeled data without ground truth together. So when using synthetic data set, they apply the ground truth, they apply the endpoint error loss between the predicted flow and the ground truth flow to train the network in a supervised manner. And then when they train, after that, they also train the network on unlabeled data. But in that case, they calculate the flow warped error between the two images. So for example, if the network correctly estimates flow, and given the flow, they warp the target frame to the current frame, and then they subtract the reconstructed frame and the source frame to get the warped error. Then if the optical flow is correctly estimated, then the corresponding pixel should have nearly zero intensity differences. At the same time, occluded pixel may have some error. So they try to capture, and then they apply the adversarial loss, that whether the flow warped error from the unlabeled data is looks similar as the warped error from the correct in the synthetic data set. So this adversarial losses guides the network to estimate correct optical flow, which warped error looks as similar as the flow warped error from the synthetic data set. So it's kind of indirectly leveraging the labeled data in using adversarial loss. So in this work, they demonstrate that they don't use any proxy loss that includes data term or smoothness loss term but only uses this adversarial loss and shows the benefit. And then here are some comparison that so the first column is the ground truth, and the second one is jointly training the network in a semi-supervised manner, like standard semi-supervised way that applying the supervised loss and also at the same time applying the unsupervised loss from some previous paper. But when doing the proposed way, they achieve much better accuracy. And so the second row shows this flow warp error map, and the networks try to estimate optical flow that induces this warped error as similar as the ground truth. So I think this is also an interesting work of overcome the limitation of the current self-supervised learning approach where the losses are handcrafted, so which the limitation comes from. So in conclusion, so we have, I presented, so there are some, I'm sorry. So in conclusion, so ill-posed problem can be solved in a self-supervised manner by using the proxy loss. So depending on the proxy loss design, we can achieve not only depth optical flow or even thin flow. So the accuracy and as well as the objective really depends on designing the proxy loss, also proxy task as well. So it matters for better accuracy, but on the other hand, it means it can be also a limiting factor that limits the accuracy. So I don't have any good solutions for now, so it's a kind of open question, but semi-supervised learning or learning the proxy loss can be another solution or another where to go to overcome the limitation of the proxy loss design that many approaches have so far. So thank you for your attentions and thank you very much.
Thank you very much for your very interesting seminar. And I think there is time for questions. So is there any question?
I may have a question.
Right.
Can you hear me? Yeah.
Yes.
So, so as far as the scene flow is caused by two types of motion, the ego motion and the object's motion, right? And I've seen that
Yes.
they have already used the weak supervision from the inertial sensors on the vehicle, like in Kitty dataset, to provide weak supervision for the POSNet in the first, let's say, set of works where they have a depth net and the POSNet. So do you think such a weak supervision can be beneficial also in the case of the scene flow network?
Yes, yes, I totally agree that weak supervision or any types of supervision that helps the networks to be trained is always helpful and beneficial. So the thing is, self-supervised self-supervision is self-supervision always depends on handcrafted design, which is always not ideal. So yes, for example, as you mentioned, like having some supplemental information from the inertial sensor can be also helpful. I think then it can help to have the correct scale. I think it helps for resolving some scale ambiguity issues.
Thank you.
Yeah, thank you.
Any other question? So I might have one which is very general, I think. So if I'm not wrong, in some of the, let's say, tasks that you considered, even if you mention the fact that, let's say, you might have the availability of maybe small sets of annotated data, but if I'm not wrong, not in all the situations, you are actually exploiting the benefit of having such a maybe small set of annotated data. So do you think how to say, how much is important to have such sets? So do you think that the self-supervision alone, maybe in some tasks, is just enough to have appropriate results? Or do you think that, let's say, the presence of a few annotated data is really fundamental in most of the cases?
So I think it depends on the task. So for example, for optical flow, so many approaches have demonstrated that self-supervision is already sufficient for sufficient in the sense that it can not only substitute the pre-training on the synthetic data set, but also the accuracy comes closer to the fine-tuning. So the thing is, optical flow is estimating 2D vector in the image space. So it's a corresponding matching task that has like a less ill-posed. However, for example, like more ill-posed problem, such as monocular flow or monocular depth estimation or sim flow, self-supervised loss is not really sufficient. So for example, if we fine-tune those, so if assuming that we have some like few labels, and if you fine-tune the network that is on trained on self-supervised manner, so if you fine-tune the self-supervised learned network, then we can get a lot of performance boost. It means that the network doesn't really fully exploit, and the network is not really, the accuracy is not really saturated yet. And this can be the current limitation that self-supervised loss can push the accuracy.
Yeah, thanks.
Yeah, thank you.
Any other question?
I also have a little curiosity. You may have mentioned this, but the talk explored different approaches, so I may have missed it. Thinking about the optical flow or scene flow estimation, I mean, I know that in classically people address the task by considering just adjacent frames, let's say. But it is what used to be the old style approach, where the computational cost of doing the actual estimation was relatively limited. I was wondering if nowadays, with the latest approaches, where you have to take into account a larger computational power at every frame, it would be possible to consider the previous estimate somehow. I'm saying it in very simplistic terms. The previous estimate as a starting point for the current estimate, considering that time continuity should help in a sense. I don't know if this is some kind of form of, I don't know, self-supervision of some kind, or maybe, I don't know, just a bootstrap to the procedure. What do you think? Does it make any sense?
Yes, I think increasing the time frame window is always beneficial, because so for instance, in the optical flow, so there has a long literature on like estimating optical flow from multiple frame, assuming the constant velocity or constant acceleration along the multiple frame. So exploiting some previous estimation, and not only the estimation, but also including some low row observed frame to the current frame window is always beneficial. So not only in the optical flow, there have been a couple of work on estimating monocular depths. that estimating, so propagating some previous estimation using LSTM has been demonstrated, and for now it has a performance, it shows some performance boost, not so significantly, but still fairly in a fair amount. So I agree that exploiting multiple frame is always beneficial.
Thank you.
Thank you.
Is there any other question? Okay, so let's thank the speaker from, let's say, this. Okay, and thank you all for attending the seminar, and see you next time.
Thank you.